Hello friends, good afternoon and welcome to EduSet Live Lectures. Dear friends, as you know that we have started a series on natural products and spectroscopy, and today we are conducting yet another lecture in the same series. In today's lecture we will talk about IR spectroscopy. To discuss this topic we have with us our subject expert Dr. Vandana. Dr. Vandana is Assistant Professor in the Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you so much. Hello viewers, in the series of natural products and spectroscopy, today's lecture is on IR spectroscopy. As we know, what is spectroscopy? Spectroscopy is nothing but interaction of electromagnetic radiation with the matter. For organic chemistry, it helps us to analyze the given unknown organic compound. What is a spectroscopy? Interaction between matter and electromagnetic radiations. Study of spectroscopy deals with emission as well as absorption spectra. Emission spectra is produced by emission of radiant energy by an excited atom, and an absorption spectrum is obtained by absorption of radiations of certain wavelength by the substance. We know there are certain characteristic features of electromagnetic radiations, among which we know that energy of a photon is equals to h nu, where nu is equal to c by lambda. So we can say energy of a photon can equals to h c by lambda, where h is the Planck's constant. So every electromagnetic radiation has a particular energy, it has a particular frequency, it has a particular wavelength, and you can see there are number of electromagnetic radiations or types of electromagnetic radiations. You can see gamma rays, X-rays, ultraviolet radiations, visible radiations, IR radiations, microwave and radio waves. If you see from left to right, for this electromagnetic radiations, wavelength, that is lambda, will increases from left to right, that is radio waves will have the highest wavelength as compared to gamma rays. If we talk about frequency, it decreases from left to right, that is gamma rays has maximum frequency. And in the same way, if we talk about energy of a electromagnetic radiation, whether we talk about gamma rays, X-rays, ultraviolet rays, visible, IR waves, microwaves, radio waves, energy decreases from left to right. That is, radio waves will have the lowest energy. Here are types of spectroscopy. You can see ultraviolet visible spectroscopy. If we are using ultraviolet radiations, IR spectroscopy, nuclear magnetic resonance spectroscopy and mass spectroscopy. All these spectroscopy we will discuss in details in coming lectures of this series, Natural Products and Spectroscopy. In today's lecture, I will discuss about IR spectroscopy. What is IR spectroscopy? As we talked about, what is spectroscopy? Nothing but interaction of electromagnetic radiations. If we take the infrared radiations, then we will say it will be infrared spectroscopy. And it includes absorption of infrared radiation by a molecule which is quantized. That is, delta E will be equals to h nu. A molecule absorbs only selected frequencies of IR radiations. That is, if there is an energy transition within the molecule. The transition involved in IR absorption are associated with vibrational changes within the molecule. So we should notice over here that only vibration changes will talk about in IR spectroscopy, which involves transition from ground state to excited state or excited state to lower ground state. Simplest modes of vibrational motion in molecule that are infrared active. Why we are saying? We are already taught that all the vibrational frequencies are not IR active. Those who are active give rise to absorptions, that is by stretching or by bending modes. You can see what is stretching when the distance between the two atoms will decreases or increases. You can see what is bended. From here you can see the bond angle will decreases or increase. Here you can say the picture presentation. However, more complex types of stretching and bending are also active, which are not shown over here. In general, asymmetric stretching vibrations occurs at higher frequencies than symmetric stretching vibrations. We must notice it. Stretching vibration occur at higher frequencies than bending vibrations. The terms other are scissoring, like scissor, rocking, wagging, twisting are also commonly used infrared bands. For example, methyl group, if we are taking, give rise to symmetric stretching vibration at this value 2872 centimeter inverse, and an asymmetric stretch at about 2962. So you can see the difference. Symmetric as well as asymmetric stretching for same group, that is for methyl group, will observed at different values. So you can easily observe these values in spectrum, IR spectrum. We will discuss in detail in coming slide what is IR spectrum. A similar phenomenon occurs in the amino group, where a primary amine, that is NH2, usually has two absorptions in the NH stretch region, while a secondary amine R2NH has only one absorption peak. So you can differentiate by this IR spectrum which one is primary amine or which one is secondary amine. There are two strong N double bond O stretch peak for a nitro group, that is for a particular nitro group there are two bands available. One is for symmetric, that is at approximately about 1350, and for asymmetric stretching for the same bond, that is N double bond O, the peak will observed at 1550. So you can observe easily the nitro group by observing these two values for symmetric stretching as well as for asymmetric stretching. And these vibrations are called fundamental vibrations. Usually the spectrum is complicated, it's not simple. IR spectrum for a particular compound or for a particular unknown thing will not be as simple. It is complicated. Why? Because the presence of weak overtone. We will discuss it in detail. What is overtone? Combination and difference band. So what are these? Overtones results from excitation from ground state to higher energy state, which correspond to integral multiples of frequency of fundamental. For example, you might observe weak overtone bands at 2V, frequency 3V, any kind of physical vibration generates overtones. If you pluck a string on a cello, the string vibrates with a fundamental frequency. However, you also observed less intense vibrations at several overtone frequencies. An absorption in the infrared at 500 centimeter inverse may well have an accompanying peak of lowering value at 1000. This is an overtone. When two vibrational frequencies, that is V1 and nu2 in a molecule couple to give rise a vibration of new frequency within the molecule, when such a vibration is infrared active, it is called combined, or we can say combination band. This band is the sum of the two interactive bands, that is nu1 plus nu2. You should observe here, or we can notice over here, that all possible combinations are not occur. Difference bands are similar to combination bands. It results in the difference of frequency, that is nu1 minus nu2. One can calculate overtone, combination and difference band by directly manipulating frequencies in wave numbers via multiplication, addition, subtraction respectively. When a fundamental vibration couples with an overtone or combination band, the coupled vibration is called Fermi resonance. It is a new name, new term, Fermi resonance. Again, only certain combinations are allowed. We should notice all the time that all the combinations are not allowed. Fermi resonance is often observed in carbonyl compounds. You know what are carbonyl compounds? Aldehyde and ketones. Although rotational frequencies of whole molecule are not infrared active, we taught this, that only vibrational frequencies are infrared active. They often couple with stretching and bending. Which one? Rotational frequencies coupled with stretching and bending vibration in the molecule to give additional fine structure to these absorptions, thus further complicating the spectrum, IR spectrum of a molecule. One of the reasons a band is broader than the sharp in the IR spectrum is rotational coupling we observed, which may lead to a considerable amount of unresolved fine structure. Unresolved means you cannot analyze it completely. Now, what is molecular vibrations? The natural frequency of a vibration of a bond is given by equation nu bar is equal to 1 by 2 pi c root k by mu, where m1 and m2 are the two bonded atoms, which is derived from Hooke's law. For vibrating springs, the reduced mass of system is given by mu is equal to m1 m2 divided by m1 plus m2. Here k is a constant that varies from one bond to another. That is, for single bond it is, if it is A, then for double bond it will be double to that of first bond. As a first approximation, force constant for triple bonds, that is K, are 3 times those of single bonds, whereas force constant for double bonds are twice those of single bond. So as well as the intensity, or we can say the triple bond increases or double bond, the K value also increases. Two things should be noticeable immediately. One is that stronger bonds have a large force constant, that is K, and vibrate at higher frequencies than weaker bonds. The second is that bonds between atoms of higher masses, or we can say larger reduced mass, that is mu, vibrate at lower frequencies than bonds between lighter atoms. How can we observe all these things? Because of this relationship, because of Hooke's law, that is mu bar is equal to 1 by 2 pi c root k by mu. In general, triple bonds are stronger than double bond or single bonds between the same two atoms and have higher frequencies of vibration, or we can say higher wave numbers. You can see over here, this is C triple bond C, double bond and single bond, and you can see the values are increasing for triple bond, for double bond as compared to single bond. And you can see over here why it is so, because of the increasing force constant, that is K. The CH stretch occurs at about 3000. As the atom bonded to carbon increases in mass, the reduced mass increases and the frequency of vibrational decreases, or we can say wave number gets smaller. Here you can see this is CH, single bond C, CO. What observe you here? From left to right, the mass of this atom will increases from carbon, hydrogen to iodine. So you can see the value decreases, or we can say mu increases. Bending motions occurs at lower energy, or we can say lower frequency. So we can talk about in any term, in energy term, in frequency term, we can talk about wave number also in the same manner. Then the typical stretching motions because of the lower value for the bending force constant. So you can see here, if we talk about carbon hydrogen stretching, the value will be 3000 centimeter inverse, and when we talk about for bending for the same carbon hydrogen bond, it will be 1340. So you can see the big difference between these two values. Now hybridization affects the force constant K. Also bonds are stronger in this order. We can say this is the order. If we talk about sp hybridization, it will be stronger than sp2. It will be stronger bond than sp3. And the observed frequencies of CH vibration illustrate this nicely. You can see this is 3300 for triple bond, or we can say sp hybridization. For double bond or for sp2 hybridization, the value will be 3100. For sp3 hybridization, or we can say if single bonds are there, then value will be 2900 centimeter inverse. Next point is resonance. Resonance also affects the strength and length of a bond. How? And its force constant K. For example, ketone has its C double bond O stretching vibration at value 1715. A ketone that is conjugated with carbon double bond absorbs at lower frequency near this. So we can say conjugation lowers the frequency value. You can see over here what kind of conjugation here, C double bond O, this is carbonyl group, and this conjugation is increased by this carbon double bond carbon, and you can see this is the another conjugated form, how the conjugation took place, and it lowers the frequency value of that particular group, that is carbonyl group. Now about instrumentation, IR instrumentation, infrared spectrophotometer. The instrument that determines the absorption spectrum of a compound is called IR spectrometer, or we can say IR spectrophotometer. Two types of infrared spectrophotometers are in common use. One is dispersive infrared spectrophotometer and another one is Fourier Transform instruments. We will discuss in both in details. Both of these types of instruments provide spectra of compounds in the common range. You should notice this 4000 to 400 centimeter inverse. Although the two provide nearly identical spectra for a given compound, then what is the difference between these two? Dispersive and Fourier Transform. FT infrared spectrophotometer provides the IR spectrum much more rapidly than the dispersive instrument. Now first, what is dispersive infrared spectrophotometer and how it works? The instrument produces a beam of IR radiation from a hot wire and by the means of mirror divide it into two parallel beams of equal intensity radiation. You can see in this figure, this is the IR source and you can see this IR source, this IR radiation is bifurcated by these two mirrors. The sample is placed in one beam and other beam is used as a difference, as a reference. You can see over here, this is the reference cell and this is the sample cell. The beams then passes into the monochromator which disperses each into a continuous spectrum of frequencies of infrared light. The monochromator consists of a rapidly rotating sector, that is beam chopper, that passes the two beams alternatively to a diffracting grating, that is a prism in older instruments. The slowly rotating diffraction grating varies the frequency or wavelength of radiation reaching the thermocouple detector. The detector senses the ratio between the intensities of reference beam and sample beams. In this way, detector determines which frequencies have been absorbed by the sample and which frequencies are unaffected by the light passing through the sample. After signal from the detector is amplified, the recorder draws the resulting spectrum of the sample on a chart. It is important here to realize that spectrum is recorded as the frequency of infrared radiation changes by rotation of diffracting grating. Dispersive instruments are said to record a spectrum in a frequency domain. Note that it is customary to plot a frequency wave, or we can say wave number, versus light transmitted, not light absorbed. You must notice this point. This is recorded as percentage transmittance. So, because the detector records the ratio of intensities of the two beams. Here you can say what will be the percentage transmittance, IS, and divided by IR multiplied by 100. What is IS? It is the intensity of the sample beam and IR is the intensity of the reference beam. In many parts of the spectrum, transmittance is nearly 100%, meaning that sample is nearly transparent to radiation of that frequency. It means it does not absorb it. Maximum absorption is thus represented by minimum on the chart. Even so, absorption is traditionally called a peak. Here you can see the graphical representation of the IR spectrophotometer. This is the IR energy source. These are the two radiations bifurcated by this mirror. Here is this reference cell, here is the sample cell, motor, this is beam chopper, and this is a detector. And after amplification, here you can see spectrum observed in the recorder, and you can see this is the diffraction grating. The chemist often obtain the spectrum of a compound by dissolving it in a solvent. So we have to dissolve the substance for which we want IR spectrum. The solution is then placed in a sample beam while pure solvent is placed in the reference beam. the instrument automatically subtract the spectrum of the solvent that of the sample. The instrument also cancels out the effect of IR active atmospheric gases, that is CO2 and water vapor, from the spectrum of the sample. This convenience feature is the reason most dispersive IR spectrophotometers are double beam, that is we can say sample plus reference instrument that measures intensity ratios. Since the solvent absorbed in both beam, it is in both terms of the ratio IS divided by IR and cancels out. If pure liquid is analyzed, the compound is placed in the sample beam and nothing is inserted into the reference beam. When the spectrum of liquid is obtained, the effects of atmospheric gases are automatically cancelled since they are present in both the beams, in reference beam as well as in the sample beam. Now, the second spectrophotometer, or we can say advanced spectrophotometer, what is that? This is nothing but Fourier Transform spectrophotometer. The most modern IR spectrophotometer operate on a different principle. The design of optical pathway produces a pattern called interferogram. What is that? It is a complex signal, but its wave-like patterns contain all the frequencies that make up the IR spectrum and is essentially a plot of intensity versus time. So we can say it is a time domain spectrum. A mathematical operation known as Fourier Transform can separate the individual absorption frequencies from the interferogram, producing a spectrum virtually identical to that of obtained with the dispersive spectrophotometer. This type of instrument is known as Fourier Transform Infrared Spectrometer, or we can say FTIR. This is the graphical representation of IR, Fourier Transform IR Spectrophotometer. Here you can say this is the fixed mirror, this beam is then passing to this moving, and this is the sample cell, this is detector, and you can say here a computer is attached to this and we will get a spectrum over here, and we can more precisely say it is FTIR, and this is the interferogram, that is the signal is computer receives. So we have discussed about the general what is IR spectrophotometer and the instrumentation about dispersive spectrophotometer. In the coming part of this lecture, we will discuss in detail about the FTIR spectrophotometer and the different values which are observed by the spectrophotometer. Thank you so much. Hello viewers, about the FTIR spectrophotometer, we already said in the last part of this lecture that it is the advanced technique or advanced instrument as compared to dispersive spectrophotometer. Here you can see the graphical representation of Fourier Transform Infrared Spectrophotometer. It is the fixed mirror, and you can see how this get converted into spectrum. By this, you can see this is the IR source, and this is beam splitter, this is moving mirror, and this is the sample cell. Here is the detector, and it is attached to then computer, and you will get a spectrum over here. The advantage of FTIR installment is that it acquires the interferogram in less than a second. It is thus possible to collect dozens of interferograms of the sample cell and accumulate them in memory of a computer. When a Fourier transform is performed on the sum of the accumulated interferograms, a spectrum with a better signal to noise ratio can be plotted. An FTIR instrument is therefore capable of greater speed and greater sensitivity than a dispersive instrument. FTIR uses an interferometer to process the energy sent to the sample. In the interferometer, the source's energy passes through a beam splitter, a mirror placed at 45-degree angle to the incoming radiation, which allows the incoming radiation to pass through but separates it into two perpendicular beams, one undeflected and the other oriented at 90-degree angle. One beam, the one oriented at 90 degree, goes to a stationary mirror and is returned to a beam splitter. The undeflected beam goes to a moving mirror and is also returned to the beam splitter. The motion of the mirror causes the path length that second beam transverses to vary. When the two beams meet at the beam splitter, they recombine, but the path length differences of the two beams cause both constructive as well as destructive interferences. The combined beam containing these interference pattern is called the interferogram. Interferogram contains all the radiative energy coming from the source and has a wide range of wavelengths. The interferogram generated by combining the two beams is oriented towards the sample by the beam splitter. As it passes through the sample simultaneously absorbs all the wavelengths that are normally found in its IR spectrum. The modified interferogram signals and reaches the detector contains information about the amount of energy that was absorbed at every wavelength, or we can say at frequency. The compound compares the modified interferograms to a reference laser beam to have a standard of comparison. The final interferogram contains all the information in one time domain signal, a signal that cannot be read by a human. So we have to convert it, and a mathematical process called a Fourier Transform must be implemented by computer to extract the individual frequencies that were observed and to reconstruct the plot we recognize as a typical IR spectrum. Computer interface FTIR instruments operate in a single beam mode. To obtain a spectrum of compound, the chemist first obtain an interferogram of the background, which consists of the IR active atmospheric gases, CO2, water vapor. The interferogram is subjected to a Fourier transform which yields the spectrum of the background. Then the chemist places the compound into the beam and obtain the spectrum resulting from the Fourier transform of the interferogram. This spectrum contains absorption bands for both the compound as well as for the background. The computer software, what will do over here, automatically subtract the spectrum of the background from the sample spectrum and yielding the spectrum of compound being analyzed. The subtracted spectrum is easily identical to that of obtained from a traditional double beam dispersive instrument. So this was about the instrumentation part of the IR spectroscopy. Now how can we prepare the samples for IR spectroscopy? Glass and plastics absorb strongly throughout the IR region of the spectrum. Cells must be constructed of ionic substance, typically sodium chloride and potassium bromide. Potassium bromide plates are more expensive than sodium chloride plates but have the advantage of usefulness that it increases the range, that is 4000 to 400. Sodium chloride plates are used widely because of their low cost. The practical range for their use in spectroscopy extends from 4000 to 650. Sodium chloride begins to observe at 650 and any bands with these frequencies less than this value will not be observed. Since few important bands appear below 650 cm inwards, sodium chloride plates are in most important use for routine IR spectroscopy. Liquids. A drop of liquid organic compound is placed between a pair of polished sodium chloride or potassium bromide plates referred to as salt plates. When the plates are squeezed gently, a thin liquid film forms between them. A spectrum determined by this method is referred to as a neat spectrum since no solvent is used over here. Salt plates break easily and are water soluble. Organic compounds analyzed by this technique must be free of water, otherwise it will give its own peak. The pair of plates is inserted into a holder that fits into the spectrometer. Solids. Three common methods for preparing a solid sample for spectroscopy. The first method involves mixing the finely ground solid sample with powdered potassium bromide and pressing the mixture under high pressure. Under pressure, potassium bromide melts and seals the compound into a matrix. This results in KBr pellets or potassium bromide pellet that can be inserted into a holder in the spectrophotometer. The main disadvantage of this method is that potassium bromide absorbs water, which may interfere with the spectrum that will you observe. If a good palette is prepared, the spectrum obtained will have no interfering bands, that is undesirable bands, since potassium bromide is transparent down to 400 centimeter inverse. The second method for solids, a nozzle mull, involves grinding the compound with mineral oil to create a suspension of finely ground sample dispersed in a mineral oil. The thick suspension is placed between the salt palette, that is potassium bromide plates. The main disadvantage of this method is that mineral oil obscures or resists bands that may be present in the analyzed compound. Nozzle bonds appear itself at 2924 value, 1462 value, 1377. And the third method used with solid is to dissolve the organic compound in a solvent, most commonly carbon tetrachloride. Although it is possible to cancel out the solvent from the spectrum by computer or instrumental techniques, the region around 785 is often obscured by the strong CCl stretch that occurs here due to this carbon tetrachloride. Now, applications of IR spectroscopy. What is the application of IR spectroscopy? It has a great advantage in identification of functional group. When you want to analyze which functional group is present in given substance, you can easily analyze by IR spectroscopy. By examining a large number of compounds known to contain a functional group, we can establish which IR absorption are associated with which particular functional group. And it is not possible merely by interpreting its IR spectrum to analyze a complete organic compound, but other evidences should be assessed like chemical, physical and spectroscopic simultaneously. Following points should be analysis in the order. We should first analyze in IR spectrum of organic compound the nature of the carbon skeleton, that is it is aromatic in nature or it is alkane, alkene or alkyne. So which kind of carbon skeleton is present in given organic compound. Then we should go for carbonyl compounds. What are carbonyl compounds? That is aldehydes, ketones, enols or carboxylic acid derivatives. What are carboxylic acid derivatives? These are acid halide, these are amide, these are ester and anhydrides. These are carboxylic acid derivatives and all these compounds contain carbonyl compound. So after analysis of carbon skeleton for a particular compound, we should go for carbonyl compound. And after that we should go for hydroxy compounds. What are these? Hydroxy compounds and the ethers. Alcohols, for example, hydroxy compound, phenols and epoxides and carbohydrates. Then next point is nitrogen compounds. For example, amines, nitro compounds, nitriles and isonitriles. All these are nitrogen compounds. Then carbon halogen bond. For example, acid halides, sulfonyl halides. Then sulfur and phosphorus compounds can contain other halogen atoms, for example, nitrogen and halogen. An IR spectrophotometer determines the position and relative sizes of all these absorption or peaks in the IR region and plots them on a piece of paper. You can see it is a kind of IR spectrum. So you can see this is the percentage transmittance from this top to bottom, or we can say bottom to top. It is this values increases from 0 to 100, and from here you can see from left to right, that is from 4000 to 400, this is the wave number which is given in centimeter inverse. So this kind of spectrum, or we can say percentage transmittance, the plot of absorption intensity versus wave number or sometimes wavelength is referred to as IR spectrum. The spectrum shows in figure exhibits at least two strongly absorption peak at about 3000 and at about 1715 centimeter inverse. So here you can see this value, this is related to, this is between 3200 and between 2800, and this is because of CH stretching, and this is because of this value approximately about 1700 to 1750. This value is related to carbonyl stretching, and this is the spectrum of 3-methyl-2-butanone. The strong absorption at 1715 that correspond to the carbonyl group is quite intense. You can see the intensity, you can see the length of this. So it is very intense peak of carbonyl peak. In addition to characteristic position of the absorption, the shape and the intensity of this peak are also unique to the carbonyl bond. So here we can say these peaks as compared to these are less intense. In fact, it is a sharp peak, and you can say this as compared to this peak, this is broader peak. So this is very intense as well as sharp peak. This is true for almost every type of absorption peak. Both shape and intensity characteristic can be described, and these characteristics often enable the chemist to distinguish the peak in potentially confusing situations. So we have to see particularly the shape, whether it is broad or sharp, or we have to see the intensity, whether it is less intense or it is strong intense. For instance, to some extent, carbon double bond oxygen, that is carbonyl group, and carbon double bond carbon, that is alkene bond, absorbed in the same region of the IR spectrum. Here you can see the range, these are similar range. However, the carbonyl bond is a stronger absorber, whereas carbon double bond carbon bond generally absorbs only weakly. So it will be a sharp peak and it will be a strong intense peak as compared to this carbon double bond carbon, although the range are same. Hence, trained observers would not interpret a strong peak at 60-70 cm to be as carbon double bond carbon. Rather, it will be interpret as for carbonyl compound and not for carbon double bond carbon bond. The shape and the fine structure of peak often give clues to its identity as well. Thus, although NH-OH regions overlaps, here you can see these are the values 3650 to 3200 for OH bond, and for NH bond it is 3500 to 3300 inverse. The NH absorption usually has one or two sharp absorption band of low intensity, and you can see here this is NH absorption, low intensity, whereas OH when it is in NH region usually gives a broad spectrum. So you can compare between these two, between NH and between OH. Also, primary amines gives two absorption peak in this region, whereas alcohols are pure liquids give only one. So here you can see the difference between NH and OH. This will you can observe a broad peak, and here it is a sharp peak. Figure shows a comparison of the shapes of absorption bands for OH and NH groups. Often when reading the literature of organic chemistry, you will find absorption referred to as strong, that is S, if it is medium it is M, and weak W, broad or sharp. How can you analyze the spectrum, or we can say IR spectrum of a compound? When analyzing the spectrum of unknown, concentrate your first effort on determining the presence as well as the absence of a few major functional group, because both will help you a lot. That is carbonyl, OH, NH, C single bond O, C double bond C, ON, NO2 peaks are the most conspicuous and give immediate structural information, whether they are present or not. Do not try, never try to make a detailed analysis of CH absorption near 3000. Almost all compounds have these absorption, that is why it should not done. Do not worry about subtleties of the exact environment in which the functional group is found. That is a carbonyl group present? The carbonyl group give rise to a strong absorption in the region 1820 to 660. The peak is often the strongest in the spectrum and of the medium width. If CO is present, check the following steps. For acids, if is OH also present along with CO, The broad absorption should be present near 3400 to 2400, which overlaps usually CH. For amides, is NH also present along with CO? Because what is the amide group? RCONH2. So we have to look for carbonyl group as well as for NH. Medium absorption, what will happen over here? For NH, for amides, medium absorption near 3400, sometimes a double peak with equivalent halves. For esters, that what is ester? RCOOR. So we can see along with carbonyl group you have to look for carbon single bond oxygen, and for that you will see the strongly intensify absorption near 1300 to 1000 centimeter inverse. For anhydrides, 2 carbonyl absorption should present, 1810 and 1760. For aldehydes, you have to see along with carbonyl group you have to also look for CH presence. Here you can see the different values for OH, for KH, for CH, for C double bond N, C double bond C, C double bond O, C double bond C and C single bond O. These are the different values you can observe for carbonyl compound along with the derivatives of carbonyl compound, that's it, acid or amide, or we can say ester, or we can say anhydride. If carbonyl group is present, check also for OH. Alcohols, broad absorption near 3400 to 3300 for alcohols. For phenols, find C single bond O near 1300 to 1000. For amines, you have to see the medium absorption near 3400. For ethers, you have to see carbon single bond oxygen near 1300 to 1000 and the absence of OH near 3400. Double bonds is a weak absorption, or we can aromatic rings, medium to strong absorption in the region 1600 to 4500. These often implies an aromatic rings. Confirm the double bond or aromatic ring by consulting the CH region. Aromatic and vinylic carbon hydrogen bond occurs to left of the aliphatic, that is CH occurs to the right of this value. In the beginning, we should resist the idea of trying to assign or interpret every peak in the spectrum. We have to look for the main peak first. Concentrate first on learning these major peaks and recognizing their presence as well as their absence, because both will give you clue about the functional group, whether it is present or whether it is absent. For example, for triple bonds, carbon double bond N is a medium sharp absorption bond near carbon double bond carbon is a weak sharp absorption near 2150. Check also for acetylenic, that is carbon hydrogen near 330. For nitro groups, you have to look for 2 absorptions, that is for 1600 to 530 and for 1390 to 300 centimeter inverse. For hydrocarbons, major absorptions are in the CH regions near 3000 centimeter inverse. Very simple spectrum, the only absorption appear near 1460 and 1375 centimeter inverse. Important functional group. The basic information about the functional group or the type of vibration is abstracted and the place in spectral analysis box where it may be consulted easily. So we will discuss it here in details about hydrocarbons. Hydrocarbons are alkanes, alkenes and alkynes. First of all, alkanes. Alkanes show very few absorption bands in the IR spectrum. They yield 4 or more CH stretching peaks near 3000 plus CH2, and that is methylenic, and methyl bending peaks in the range of 1475 to 365 centimeter inverse. CH stretching vibration occurs at 3000. In alkanes, sp3 hybridization, CH absorption always occurs at frequencies less than 3000. If a compound has vinylenic, aromatic, acetylenic, cyclopropyl hydrogens, the carbon hydrogen absorption is greater than 3000 centimeter inverse. Methylene group have a characteristic bending absorption at approximately 1465. Methyl group, that is CH3 group, have a characteristic bending absorption of approximately 1375 centimeter inverse. The bending for this methylene group, or we can say rocking motion associated with 4 or more methylene group in an open chain, occurs at about 720 centimeter inverse. So we have to look these values for alkanes of which kind of acetylenic or which kind of alkane present in a given organic compound. Next hydrocarbon is alkenes. What is alkene? Nothing but carbon double bond carbon. Alkenes show many more peaks than alkanes. The principal peaks of diagnostic values are CH stretching peaks for sp2 carbon. When we talk about alkenes, the hybridization will be sp2. So we have to look for sp2 carbon at values greater than 3000, along with carbon hydrogen peaks for tetrahedral, or we can say for alkanes, or we can say for sp3 hybridization atoms, carbon atoms appearing below that value. Also bending peaks that appear in this range 1000 to 650 centimeter inverse. For unsymmetrical compounds, you can see what is unsymmetrical. When different groups are attached to this carbon double bond carbon, it will be unsymmetrical alkenes. You should expect to see the stretching. What is kind of stretching? Carbon double bond carbon near 1650. Here you can see the IR spectrum of decane. This value is related to this sp3 CH stretching, that is these CH3, these values, and this is the methylenic band. This is CH2 you can see, or CH3 band, and this is long chain band. This is another spectrum of cyclohexane. Here you can see in this spectrum you can see sp3 CH stretching, and this is CH2 band, and this is no long chain band over here. So you can compare with this cyclic compound and with this open chain compound according to this IR spectrum. Now alkenes. The CH stretching for sp2 CH occurs at values greater than 3000 centimeter inverse. CH bending occurs in the range of 1000 to 650. These bands can be used to determine the degree of substitution on the double bond. Carbon double bond carbon stretching vibration occur with this value, and conjugation, what happens? Conjugation moves this value to lower frequencies, we have discussed in detail in the earlier slides, and increases the intensity of the peak. Symmetrically substituted bonds, for example 2,3 dimethyl 2-butene, do not absorb in IR because there is no dipole moment change. So for a peak to be IR active, it has to be a particular dipole moment. Symmetrically di-substituted trans double bonds are often weak, cis are stronger. For example, this you can see these are the spectrum of alkenes. This is 1-hexene and this is cyclohexene. Here you can see this band is related to this sp2 CH stretch. This is for sp3. This is a overtone. You can see the intensity, you can see the broadness also. This is a sharp peak as compared to this. And here you can see the IR spectrum of cyclohexene also. This is sp2 CH region. This is sp3 CH stretching. This is for cyclohexene. So we have discussed about the IR spectroscopy fundamentals, which kind of spectrum is there. We have discussed about the instrumentation, and we have discussed about which kind of IR spectrum will probable in case of hydrocarbons, that is alkanes, alkenes and alkynes. Hope you understood this lecture. Thank you so much.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Vandana for coming here and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.